Thank you for joining. And now I've got to hand over to the Maths in Space panel with Dr. Jane Mcarthur. And I can see someone on my screen. Jane Mcarthur, you are there. I can see you.
Thank you very much, John.
You're above the clouds.
Fun listening to some of your panel. And this is Antarctica, where we collect meteorites, or at least other people collect meteorites. So I just thought I'd freeze the background down again, even though we're heading into spring.
Super. Best of luck.
Thank you very much. Right, so I think I can see both Megan and Catherine. So we're here to talk about maths in space today. Last but by no means least, the mathematics underpins everything that's gone before in the technology and science panels you've been hearing about. And we'll tell you about how our journeys have used maths to get us to where we are today and the different things we are studying. So my name is Jane Mcarthur. I'm currently a postdoc researcher at the University of Manchester. I'm looking after the UK Antarctic meteorite collection. So my boss arranged 2 expeditions to Antarctica and managed to bring back 120 rocks that we think are meteorites. And it's my job to curate the collection and to try and classify them all, because we always like to stick labels on things, try and group together the ones that are similar and the ones that are different, try and work out what makes them different. Did they form at different places in the solar system? Most meteorites come from somewhere in the asteroid belt today, but has the asteroid belt always been in that position? Did they form in that position? What impact events have they been through? So meteorites can tell us an awful lot about space, and they're the only samples we have on Earth other than a few sample return missions that have been put together by the space agencies. So we use these meteorites, we use little fragments of them to make polished blocks or thin sections, and then we can look at them with powerful microscopes to determine what elements and minerals these rocks are made of. And the different abundances of chemical elements in those is largely how we start out a classification scheme to group together meteorites that probably came from the same parent body out there somewhere in the asteroid belt. But before I talk too much about myself, I'd like to introduce the other panelists. So if we could go to Catherine first and hear a little bit about what she's studying today.
Hi everyone, so I'm Catherine. I'm a PhD student, so I'm still studying, and I am based at the Millard Space Science Laboratory, which is one of the departments of University College London. So my research is based on Mars, and I use this satellite, which is my background, Mars Express, and I use one of the instruments on this satellite to collect data about the plasma and the kind of magnetic environment of the kind of very high levels of Mars's atmosphere, which is really exciting. So my research at the moment is looking at a dust storm on Mars. So every kind of now and then we have these global dust storms where the whole planet is covered in dust in one gigantic storm system, and I'm using this satellite to look at how this storm has influenced the really high levels of the atmosphere and look at the ions and electrons and see how they behave during this storm period. So I'm in my second year of my PhD, so I've got about another year and a half left, but it's really, really exciting, and I love working on Mars.
That's really fascinating. Can I just get a quick question in there with the differences between the magnetospheric environment of Mars to Earth? Because that's partly why we see very different things on Mars, isn't it?
Yes, so at Earth, we're really lucky in that we have a global magnetic field. So this protects us from some of the really harsh radiation that the sun is constantly emitting in the form of the solar wind. So we have this kind of invisible bubble that protects us, which is fantastic. It keeps our atmosphere there and keeps us alive. Whereas Mars does not have this. There is no global magnetic field. There's nothing kind of producing this in the center of Mars. So it's kind of exposed to the solar winds. The solar wind can travel really, really close to Mars and strip away what's left of the atmosphere. So this is an ongoing process where the atmosphere of Mars is being lost, and we think that during these global dust storms there's more atmosphere being lost, and that's something that I'm researching.
Sure, that's really interesting, and obviously has a big bearing on exploratory missions that may go in the future, whether robotic or human missions. So Megan, that might be a good point to pick up with you, because you look at space weather throughout the whole solar system, I think, and the influence of the sun, which obviously affects everything. So tell us a bit about that.
Yes, thank you, Jane. So hi, I'm Megan. I'm a postgraduate research student or PhD student at the University of Exeter. I'm based in the mathematics department, and I look at what's called coronal mass ejections. So these are large expulsions of plasma that come out from the sun, big balls of mass, and they drive what's called space weather across the heliosphere, which includes our solar system. It's this big bubble-like outflow of the solar wind, as Catherine mentioned. So particularly on Earth, we get space weather can include things like seeing the aurora, but it also has impact for things like satellites, aviation, ground-based observations, but also things like our national grid. So unfortunately, Mars doesn't get the same impact as we do on Earth and in some of the other planets, because obviously it doesn't have the same globalized magnetic field. But my research is based on observing these coronal mass ejections.
That's great. And so for my little party trick, this is one of the meteorites that was collected in Antarctica by my boss. And just to give you an example of a meteorite, this is not from Antarctica, I hasten to add, but this is an iron meteorite. You may have had an opportunity to see one in a museum or a collection at one point. And this is really quite heavy. It's like iron nickel from the core of an asteroid. This is what we think formed in the asteroid belt early on, where something didn't get big enough to become a planet, but it was big enough to have the iron nickel separate into a core. And so these are some of the rarer meteorites. We don't have an iron meteorite in the UK Antarctic meteorite collection yet that we know about, but we do have some mesosidereites, which are from another layer, more between the crustal layer and the core layer. We've classified about 30 meteorites to date, and we've got about another 50 ready to go in shortly. However, I'll talk a little bit more about my Martian background, because my PhD studies were at the University of Leicester, where I studied the first of a new type of Martian meteorite. It was thought to be a breccia, which was thought to be a fusion of different surface material on Mars. And we hadn't had examples of the surface before. We'd had sort of volcanic rocks, which we thought formed at depth. But this new breccia was thought to have been fused from lots of different bits of Mars on the surface in one giant impact event, and then lifted out of Mars in another impact event. And it was first characterized in a paper in 2011. And I picked it up for my master's project, and then it became a PhD project in 2014. And we examined it with all kinds of microscopy techniques, scanning electron microscopes. And we went to one of the UK flagship facilities, the Diamond Light Synchrotron, where you can get resolution right down to the finest microns and very small scale to study your science. And we were interested in seeing the minerals in the meteorite, if they contained water, and if this gave us some insights into the history of water on Mars, which is a big topic because obviously water is needed for life. We did find some hydrated iron minerals, but we are still not sure if the water content was added when it was on Mars or after it was ejected from Mars and when it landed on Earth. And we need some even more detailed studies which would look at the oxygen in that water content to see if the water ratio is like Mars or terrestrial water. So we're still waiting for a result on that. But so that's from the Martian background. I was also looking at some comet samples from NASA's Stardust mission and comparing them with carbonaceous chondrite materials. So I already had a few different materials from my PhD background, which made it really interesting to go into the curation job, where I'm looking at a whole different world of many different meteorites. So how does this relate back to maths? Well, maths sort of underpins many things that we all do on a day-to-day basis in our jobs, because whenever you're looking at data sets, you have big data sets that you need to reduce down. Sometimes you might need to learn some computer programming to sort of rationalize numbers. You might want to use programming to plot graphs, to normalize data, to look at the significance of the data. You're using the standard deviation and some other things you first learn in statistics at school. So all of these things come together in our day-to-day jobs. But maybe, Catherine, you could explain how maths has been involved in your journey to where you are now.
Yeah, of course. So when I was at school, so back in secondary school, I really loved maths and really enjoyed it. I think I was probably one of the few people that really enjoyed it at school, but I was always quite good at it. So I never kind of thought about it career-wise, but it was always something that I had alongside with me, that I knew that I could do well. But the subject I really enjoyed at school was geography. So when I was kind of thinking about university options, I ideally wanted to do something with geography and physics and maths, because those were the A levels I chose. And I ended up doing a degree for my undergraduate at the University of East Anglia in environmental geophysics. I didn't think I wanted to do pure physics. I wasn't in top set science at school, so I didn't think I was clever enough to do physics or astrophysics. So I focused on Earth to start off with. I didn't start off in space. I did Earth volcanoes, earthquakes, tsunamis, and absolutely loved it. And there was lots and lots of maths behind all of this. So we did fluid dynamics, so looking at how tsunamis flow and how they travel across the Earth and how this can be used to kind of help give warnings for tsunamis. We did lots of kind of seismology, so looking at earthquakes and how we can detect earthquakes and how the waves travel through the Earth and get to different detection points. And then looking at the different flows of like lava. So if they were really kind of runny flows or if they are hard flows, we looked at how we can use maths to model these different things. I also did kind of solid mechanics as well, so looking at gravity and things, but everything was very Earth-based, because that's what I was focusing on. Luckily then I had a fantastic supervisor who, once I was talking to her, I was saying, I find all this interesting, but I haven't really found what I want to do yet. And this is kind of the second and third year of uni, so we're getting quite late on, and I thought I should probably know what I want to do by now. And she suggested, well, why don't you take all of this maths and physics you've been doing for Earth hazards and do it to another planet? I didn't think I could do that. Didn't know that was a possibility because I'd not done physics or astrophysics. So I then started using modelling to make a 3D model of the pressure and the different tension and stresses on volcanoes on Mars. So this involved looking at loads of different equations, looking at how Mars has different gravity and how that affects the pressure of rocks, bringing together all these different skills, and used that for my undergraduate project. And then I went on to study for a master's in planetary sciences, where I thought I can kind of get to know some more of the solar system, because all of my stuff had been Earth-based. So here I learned about plasmas, which I'd never knew existed before my master's. I learnt all about the kind of mechanics of how plasmas work and how they travel throughout the solar system. And now I've kind of gone between those two different areas, and I look at the kind of magnetosphere, the induced magnetosphere of Mars. So lots of kind of electricity and magnetism equations, still some kind of fluid dynamics, and all sorts of different things coming together to do what I do now.
Sure, that's really interesting. I think a theme from some of the panels earlier today as well, we're kind of showing how multidisciplinary space is and how you need lots of different bits of different things. And it is perfectly reasonable to go from looking at things on Earth to looking at volcanoes on Mars, but then to be looking at magnetospherics and plasmas. And there is no such straight line or typical journey, but people tend to specialize into what they find most interesting. How was your route, Megan, using maths in
Yes.
areas?
So I'll go right back to sort of GCSE and A levels. So A levels, I was pretty good at maths. I liked maths, and I had a fantastic maths teacher. So I decided to do maths, physics, further maths, and I'm Welsh, so I also did the Welsh Baccalaureate, which for English and Scottish Irish students potentially watching, it's kind of like a holistic qualification that's coursework based that gives you quite a broad spectrum of skills. And I applied to the University of Exeter for maths amongst a few other universities, and decided to come to the university thinking I was going to do pure maths, and I loved pure maths, and this is where I was going. And I got through to my second year and I realised that I was really much more of an applied mathematician, and we have a fantastic applied mathematics department here at Exeter, and I was really, really interested in fluid dynamics, so how fluids move, how you model that mathematically, and how we can understand fluids through maths. And as I progressed through that, I had a real interest in fluids with magnetic fields, so plasmas, and I started then looking at options further down the line. I knew I wanted to do the 4-year integrated master's degree, which basically means instead of doing a 3-year bachelor's and a separate master's, you do it all in one go in the straight 4 years, and you just come out with a master's at the end of it. And I did a really specialised master's. So I have an MSci in mathematics, specialising in geophysical and astrophysical fluid dynamics, which is quite a title, but it sums up quite nicely what I did. So I got to learn a lot about fluid dynamics in the Earth's atmosphere, atmospheres and oceans, the climate system, but also magnetic fields and fluid flows. And then my master's project was looking at coronal mass ejections through multi-spacecraft. So there are lots of spacecraft we have in the heliosphere that take images of various objects like the sun, which is what I'm interested in, but also of other planets. And we also observe plasma in situ. So we measure things like the magnetic field, its composition. So I use a variety of those spacecraft to look at coronal mass ejections. But my master's project was mainly based on imagery and using geometry to basically get a more 3D feel of how these objects are moving and propagating through space. And I was really lucky that I got a research internship one summer at my university in fluid dynamics, and then I got introduced to a fantastic senior academic in my department, and she got me really interested in space weather, and I applied for a PhD in space weather looking at coronal mass ejections, which is funded by the Science Technology Facilities Council. So I'm still doing maths, still at Exeter, but applied maths and physics, there's quite a lot of overlap between them, and it can vary very much between universities as to which department you might end up sitting in.
Thanks, Megan. That's, again, really interesting, and another way to travel into the space arena. Going back, I realised I didn't cover my own A-levels. I did maths, further maths, physics and chemistry, quite a traditional combination back then. It's also partly, if you don't know what you want to do, then it's a good way to explore the subjects and find out which one you maybe like best. They support each other quite well, so it doesn't leave you with gaps later on. My school only offered further maths on a half timetable basis because it was a state school. So in a way, this is quite a preparation for university because it's quite intense lessons, and then you had to go and figure out what they were all about in your own time. I thought originally I might apply for university for physics, but I realized as application dates grew near that I actually preferred mathematics. So I ended up doing mathematics at the University of Nottingham. However, I kind of drifted towards more statistical modules, and back when I did it many years ago, planetary science was barely a field, and I didn't even know there were jobs available in it back then. There was just about some astronomy going on, but the fields have developed so much in the last 20 years, it was very different. So I ended up with the biggest graduate recruiter, qualifying as a chartered accountant and working for some years. I ended up at the final space shuttle launch in Florida in 2011, which was an amazing occasion. And I came back to England kind of thinking, oh, why isn't there more space going on? Or isn't there a way to get involved? And then I found several conferences, talks, meetings. I discovered there's a field called astrobiology by attending some talks at University College London. And the following year, I found myself enrolled in the Masters in Planetary Science there. I think that's the same one that Catherine did. So over 2 years, I tried to fill in all the knowledge gaps because some of my modules were fourth year physics modules or fourth year earth science modules, and I hadn't done the first 3 years of either subject. So there were a lot of knowledge gaps there, but the maths kind of stood me in good ground for catching up on the physics equations and making sense of what I was seeing. And again, it was an internship in the summer in the Masters that I was working on some of the first data off the Curiosity rover with one of the two scientists in the UK, Professor John Bridges at the University of Leicester. And he suggested I could start working on this Martian meteorite for my Masters project. And then I later applied for the PhD and ended up at Leicester for 4 years studying it. But again, it's just many different subjects can lead you in different directions, and it's best to sort of follow what you like best. But if you can do other subjects that back them up, that's also really useful, because I know people that went to study physics at university that didn't have maths A level kind of, they had to do more extra work to sort of support their studies, I think. So I think we've got a few questions in the chat. So I'll take one quickly first. How do Martian meteorites achieve escape velocity? You do need a really large impact for it, but because there's less atmosphere on Mars, the escape velocity isn't as bad as it would be on Earth. And also this is the reason that we think we probably won't find any meteorites from Venus, because the Venusian atmosphere is so thick, you would need very, very large velocities. And also because it's closer to the sun than us, it's more likely that any meteorites from Venus would be sunbound if it was possible to have an impact that big. But Martian meteorites, we do have quite a collection. I think there's around 120, probably heading towards 150 known Martian meteorites, because the number keeps creeping up every year. So a question from Charter School East Dulwich, Dr. Cooper. Do you want to go to Mars? I'll throw this to Megan first.
Honestly, I love studying the sun and space, but I cannot think of anything worse than actually going to space. It's not for me. I take my hat off to those who really want to be an astronaut, but I do not.
How about you, Catherine?
I agree. I don't. I think in terms of going to Mars, as much as it would be fantastic to see that, it would be like this generation's Apollo, being able to watch on TV people going to Mars. I would love that in my lifetime. I just think there's still so much science that needs to be done beforehand. So we've mentioned that Mars has an induced magnetosphere, which is very different to what we have at Earth. So it's really exposed to the really harsh radiation from the sun. So that's a huge risk, getting all this radiation once you're at Mars. There's also no oxygen. We don't think any liquid water. We know there's ice caps and there has been liquid water in the past. It's very cold. I mean, the list goes on. It doesn't sound like a particularly nice place to go and stay. So I'm quite happy studying it from a distance. But yeah, I'm not fussed about going to Mars.
I think I heard this question go to one of the other panels earlier, and I'm sorry we're not as enthusiastic as they were, but I've always said in answer to do I want to be an astronaut that I would like to have a remote control car on Mars that I could drive my own little rover around. I'd like a remote control boat on Titan, one of Saturn's moons, because it would be a fabulous place to be. And I'd like to kind of put my feet up in the Caribbean one day, because I think Earth is the sweet spot of the solar system, really. But and the other shout out for that is the clouds of Venus could potentially be a place to live. I mean, if you could get over all the toxic chemicals and other things, apparently sort of the gravity and the other things could just about work on in the clouds. But I don't think you want to live there for long. Visit for 20 seconds, maybe. Anyway, great question. So from Year 8 St. Peter's School, Wolverhampton, which planet is your favourite and why? Megan, any thoughts? Oh, sorry, Catherine.
That's okay. Well, I can't not say Mars, really. It's Mars Day, and I study Mars as what I do day to day. I think one of the reasons why I love Mars so much, I mean, the reason why I started studying it was purely by chance, because at university I was working with people that are experts on volcanoes on Earth. So I then started looking at volcanoes on Mars. So that was purely coincidence. But I think the reason why I've continued to study it now for three or so years is there's just so much available at Mars. I mean, it is the most explored body in the solar system apart from Earth. We've got so many satellites, so many rovers, that there is constantly new pictures, new amounts of data, new things to be explored. And although we do know a lot about Mars, there is still so much more we can find out. And I think that's what I find really exciting. And it's always nice to be able to see pictures of what you're doing as well, and seeing pictures from the Mars surface from the rovers never gets boring.
Sure. So Megan, your favorite planet, or should we allow you to say the sun if you want, because that's your area of study, but your thoughts?
Yeah, I mean, I guess Earth and the sun are kind of my favorites and what I study, but if I have to pick another planet, I would actually say Venus. It's the one that at school, when we had to pick ones to study, I always picked Venus. And also of the Holst's Planet Suites, if any of you are familiar with that music, Venus is by far my favourite piece, which kind of coincides quite nicely. So yeah, after the Earth and the Sun, I'll go with Venus.
Well, my favourite planet changes on pretty much every day of the week, I think. And yeah, that Holst music, I played it last with Leicester Symphony Orchestra a few weeks after, on the same stage I'd received my PhD a few weeks later by bizarre coincidence, because I played the violin. Again, I'm not sure which movement's my favourite off the top of my head. I have to think on that one for the music. But I'm going to give a shout out here to Uranus, because one of my very first experiences after coming back from the final space shuttle launch, I managed to get a place on the Alpbach Summer School, which was in Austria. And they send 60 science and engineering students from across Europe to work on space missions intensively for sort of 15 days with many expert tutors. I think of something like 20 experts were delivering lectures or working with the teams throughout the week, and there were only 60 of us. So it was an amazing sort of experience. So we had 4 teams of 15, and we had to design missions to the outer planets. They did try and bias us a bit, I think, towards the icy giants rather than Jupiter and Saturn, where we know more. So I think the teams, there were 2 missions to Uranus. I was on one of those, and 2 missions designed to Neptune and Triton. But things we know so little about these planets, but basically Voyager has visited them once and that's it. And it's such a long journey to get there. It's sort of 15 or 20 years journey, and that's after you've made a mission, which is sort of 10 years. So even if they start making one now, I'll be retired by the time we see anything from it. So of course, the other argument is maybe we should work on the areas we can explore better. As you say, we've got so much high-tech instrumentation at Mars, we're learning phenomenal amounts there, and it's more reachable to get to Jupiter and back to Saturn. But perhaps there'll be some game-changing technology that will help us get to the outer planets faster, because I think there's many secrets at Uranus and Neptune to learn, because Uranus is kind of 90 degrees on its side. They think it's got knocked at some point. Did it form in the inner solar system? Did it get knocked out when they think Jupiter migrated? There's all kinds of mysteries with the dynamics of the planets, and I think knowing more about those further out ones will teach us more in the future. So we've touched on a couple of internships and experiences. One other question I had was, how have extracurricular activities helped you to get to where you are today? I mean, we all talk about our work and do a lot of education outreach opportunities when we can, but also summer schools, internships, memberships of student societies and so forth. So yeah, Megan, have you got some thoughts on what you've done?
Yes, definitely. So I think there are a few main ones for me that I can pinpoint that were really helpful. So between my 3rd and 4th year of my undergraduate, I had a research internship, but also I attended a Plasmas at Paris summer school, which really helped. It was aimed at European students, so actually was opened internationally to help make that transition from bachelor's to master's and learn more about plasmas. But also there were some people in masters in Europe are a bit different, they're a bit longer, so some people, students in that, and that was really helpful. But also the big thing for me since starting my PhD has been the Royal Astronomical Society. So I currently chair the Early Careers Network, which basically supports early career academics, so PhD students and people who've just finished their PhDs who are trying to make it in academia. And through that, I've met some wonderful people, including Jane. And I've also then been able to, through that Early Careers Network, through the organising of events, I've also was nominated by a colleague for an award with the British Interplanetary Society. So I definitely say make sure to get involved as much as you can if this is something you're really interested in. All of those networks and connections not only help you find kind of a place in your community and make you feel welcomed, but they also provide an invaluable source of support and helps you find more opportunities. The more connected you are and the more you put into something, the more you tend to get back out of it.
Definitely. And Catherine?
Yeah, I think basically everything Megan said was really good advice. But also I think work experience is just really vital in just understanding what you want to do. When I was at school, because I kind of wanted to go towards geography, I thought I was going to end up in meteorology, so weather and climate change. So I spent 2 weeks on a placement at the National Grid in their climate change team. It was a fantastic week. I learned a lot about how big companies like National Grid are working towards climate change and sustainability. But after that 2 weeks, one of the most important things I learned was that I didn't want to do that. And that wasn't anything to do with them or anything to do with the placement. I just knew that wasn't the right fit for me. And over the kind of next few years being at university, I did various bits of work experience. I did some geophysical surveying, so that's kind of like in Time Team when they go out and use the magnetometer to map the subsurface. I did some of that, whereas I didn't enjoy that. And it's just about kind of crossing things off and thinking, okay, I know I definitely don't want to do that. So that narrows the field a little bit. So that definitely helped me kind of end up where I am now. And as well as that, yeah, societies are fantastic just to kind of get involved with and just meet loads of people. Unfortunately, since starting my PhD, I've not been able to kind of go to lots of conferences and meet anybody because it's all been in COVID. But there's lots of people that I'm ready and willing to meet once we're allowed. And that's just through going to kind of seminars online. Twitter is absolutely fantastic for networking. I never appreciated that before. I kind of stayed in academia, but Twitter's a great place to kind of know what's going on in the world of science, and STEM in particular. But I think just, yeah, putting yourself out there and just asking people for advice. And a lot of the time when I got kind of work experience placements, it was just because I rang someone up and said, I'm willing to learn. Do you have anything for me? And the worst thing they can say to you is no. And at least you've tried. So yeah, that's what I would say.
Yeah, I think that's a really important point you've made there about narrowing down options, because the trouble is it's awfully easy when you're sort of 16, 17, 18 going, I don't know what I want to do. Why haven't I picked the thing I'm going to do for 30 years yet? And it's because, well, firstly, you don't have enough information to make the decision. And secondly, your likes and what you find interesting may change or sort of filter down. So it's actually ruling things out is one of the valuable things that helps you get to where you want to be. I'll just make a bit of a mention of sort of the travel opportunities I've had as part of my PhD, and because I was really interested in field work, I'd taken part in the Austrian Space Forum's one of their early Mars analog missions. There's also places in Utah and Hawaii that do this. They sort of have simulations for 2 weeks of sort of trying to put some experiments down as if you were on Mars and then see what goes well, what goes badly, with sort of minimal comms or time delayed comms and a control center and things like that. But I also had opportunities to go to a summer school in the Azores and another one in Tenerife to look at volcanoes and study them further, as well as impact craters. Because, of course, when meteorites strike the Earth, most of the time we don't get a meteorite crater. But when we get the iron and the heavy dense meteorites, we do sometimes get a meteor crater. And the best preserved one is in Arizona. It's called Meteor Crater. And there's a field camp that runs there once every 3 or 4 years. And that was really fascinating. I also went to some tiny impact craters out in Estonia where they ran an astrobiology summer school. And these experiences of meeting other students from across Europe, sort of 30, 40 students. We had some lectures at the Kali summer school. We did little bits of field work, or they showed us kind of what they were studying themselves out there. And it was all really interesting. So we better get back to the questions and take a few more before we finish. A quick one from Paddockwood Primary Academy. How many meteorites have been discovered on Earth? So we have this thing called the Meteoritic Bulletin, where meteorites go before a classification committee and someone checks the scientific data and says, yes, these meteorites are ordinary chondrites, or they are from the moon or possibly Mars. And there's over 50,000 on there. NASA have been sending an expedition to Antarctica every year since I think even the 60s and certainly the early 70s. And there's this huge collection of quite pristine, because they're picked up with sterile instruments with minimal contamination and minimal weathering. So they're in really good condition for other scientists to later request samples to do special science work on them. So what else do we have here? How big is Mars? Is it about a third of the Earth? Help me out here, you Martian experts.
Yeah, roughly about a third-ish. So the radius of Earth, I think, is about 6,300.
You've even got numbers. That's impressive.
That's complete. I should know that. But I think it's about that, and then Mars is about 3,800-ish. So kind of half-ish. I don't want to say numbers exactly because I'm probably going to get them wrong. And as a Mars researcher, I should know that. So apologies. No,
that's fine. I did have the numbers when I was doing my PhD, but they've fallen out of my head right now. But that's about right. It's smaller than the Earth by quite a factor. So why does Earth have an atmosphere but Mars does not? Is that one for you, Catherine?
Yeah. So Earth, we are really lucky in that our core is kind of moving, and this is generating a magnetic field because the rock has got iron in it. So this movement of magnetic material creates a magnetic field, and it's really big, and it covers the whole entire planet, and it creates a kind of invisible force field that deflects a lot of the really harsh solar wind radiation around the Earth, and this keeps our atmosphere in, keeps it kind of tucked in, and life continues on Earth. So the core of Mars, we don't think it is, well, it isn't moving. There's no generation of a magnetic field at all. So it doesn't have this invisible force field protecting it at all. There is a bit of an induced magnetosphere. So when the solar wind reaches Mars, there are some ionization processes once the solar wind reaches the atmosphere. So it induces a very small magnetic field, but it's a lot closer to the surface, and it's nowhere near as strong as Earth's. So the solar wind reaches Mars, causes this ionization, and it gives part of the atmosphere, the upper levels of the atmosphere, lots of energy, and this means that atmospheric particles can then escape off into space. So we think this has been happening for about 4 billion years. We think that 4 billion years ago there may have been a global field like there is at Earth, but why this disappeared, why it's not there anymore, is still up for debate. I mean, there's tons of theories as to why this global field we think has gone. So that's a really interesting area of research that covers all sorts of aspects of space and science.
Great. And a quick one from Clacton County High School that I think you nearly just covered anyway. What is the core of Mars composed of? Now, I think it's like the core of our planet and others that we know, which have an iron nickel solid center. But I think the fact you were getting at, it probably doesn't have, we think the Earth has a liquid layer, which is what helps to keep our magnetic field active, I think. Whereas on Mars, we think this is probably long since frozen or lost its heat. So, and that's why the solar wind's been able to strip away. Will Earth ever be hit by a meteorite soon? Well, so the Earth is being hit by meteoritic material every single day. Oh, it's time to hand over. We are just on the way out. So meteoritic material hitting the Earth every day, falling in the oceans, and it's just not all of it survives to hit the surface. It's only now and then we get a piece that's big enough to actually make it all the way to Earth and not just burn up in the atmosphere. Thanks very much for attending today. It looks like we need to hand back to the Space Park studio, where I think there are more talks ready for you. Thank you very much.